Welcome to Elevate Learn. In this comprehensive tutorial, we'll explore Python dictionaries and sets, two fundamental data structures that power most Python applications. Whether you're building web applications, analyzing data, or creating algorithms, mastering these operations is essential. We'll start with dictionary basics and progressively move to advanced techniques, then explore set operations and their mathematical applications. By the end of this tutorial, you'll understand how to manipulate, combine, and optimize these data structures for real-world scenarios. Let's dive in. Let's start with dictionary fundamentals. A dictionary is a collection of key-value pairs, where each key maps to a specific value. You can create dictionaries using curly braces with colon-separated pairs, or using the dict constructor. Keys must be immutable, typically strings, numbers, or tuples, while values can be any Python object. Accessing values is straightforward. Use square bracket notation or the get method. The get method is safer because it returns a default value if the key doesn't exist, preventing key error exceptions. Remember, Python 3.7 onwards maintains insertion order, making dictionaries predictable and useful for many scenarios. Let's explore more operations next. Now let's explore core dictionary operations. You can add new key-value pairs by simply assigning them, or use the update method to add multiple pairs at once. For deletion, you have two options. Del removes the key and raises an error if it doesn't exist, while pop is safer as it allows a default return value. Checking key existence with the in operator is faster than using get with none. Iteration is crucial. Use items to get both keys and values, keys for just keys or values for just values. Understanding these operations enables efficient data manipulation. Let's look at more advanced dictionary methods next. Let's dive into advanced dictionary methods that can significantly improve your code efficiency. The setDefault method is incredibly useful. It returns the value if the key exists, or sets and returns a default value if it doesn't, all in one operation. This eliminates the need for conditional checks. The clear method is straightforward for emptying dictionaries. Copying deserves attention. Shallow copy creates a new dictionary but references the same nested objects, while deep copy creates entirely independent copies. This distinction is critical when working with nested structures. The FromKeys method efficiently creates dictionaries with consistent initial values. These methods are essential for writing clean, professional Python code. Dictionary comprehensions are a Pythonic way to create and transform dictionaries elegantly. The syntax is straightforward. Use curly braces with a key-value expression, just like list comprehensions. You can add conditional filters to include only specific items. This is particularly powerful for transformations, swapping keys and values, filtering based on conditions, or combining data from multiple sources. Nested comprehensions allow you to create multi-level dictionaries in a single readable expression. These techniques produce cleaner, more maintainable code and are often more efficient than equivalent for loop approaches. Mastering comprehensions significantly elevates your Python expertise. Merging dictionaries is a common operation in real-world applications. Python 3.9 introduced the merge operator, which creates a new dictionary combining both without modifying originals. This is elegant and readable. The update method modifies the original dictionary in place, useful when you want to consolidate changes. When merging multiple dictionaries, later values override earlier ones with conflicting keys. You can also use dictionary unpacking with the double asterisk operator, which works in earlier Python versions. For complex merging scenarios with custom conflict resolution, you might need to iterate through items and implement custom logic. Understanding these approaches gives you flexibility in handling diverse data consolidation requirements. Sets are unordered collections of unique elements, fundamentally different from dictionaries and lists. You create sets using curly braces with comma-separated values, or convert iterables using set. A critical gotcha: empty curly braces create a dictionary, not a set. Use set for empty sets. Sets automatically eliminate duplicates, making them perfect for deduplication tasks. Because sets are unordered, you can't access elements by index. However, this trade-off enables incredibly fast membership testing and powerful set operations. Sets store only immutable objects. You can include strings, numbers, and tuples, but not lists or other mutable types. Understanding these fundamentals is essential before exploring set operations. Sets excel at mathematical operations. Union combines all elements from both sets, giving you the complete collection. Intersection finds common elements useful for filtering data. Difference shows what's in one set but not another, perfect for identifying unique items. Symmetric difference finds elements in either set but not both, useful for comparing datasets. Each operation has two syntaxes. Operators like and are concise, while methods like union and intersection are more explicit. You can also chain operations. Set_A, set_B, and set_C. These operations run efficiently due to set implementation using hash tables. Understanding when to use each operation is crucial for writing efficient data processing code. Set modification methods provide fine-grained control over set contents. The add method inserts a single element, while update can add multiple elements from iterables. For removal, choose carefully. Remove raises an error if the element doesn't exist, while discard silently succeeds regardless. This makes discard the safer choice for defensive programming. The pop method removes and returns an arbitrary element, unpredictable but sometimes useful. Relationship checking methods are powerful for validation. Isubset checks if all elements of one set are in another. Isuperset is the inverse, and isdisjoint checks if sets have no common elements. These comparison operations are efficient and foundational for set-based algorithms and data validation logic. Set comprehensions provide an elegant Pythonic way to create sets with filtering. The syntax mirrors list comprehensions but uses curly braces. Conditional filtering with if statements allows you to select only elements meeting specific criteria. This automatic duplicate removal is one of set's most powerful features. Converting a list to a set instantly eliminates duplicates while creating a new collection. You can transform elements during comprehension, applying functions, string operations, or calculations. Combining transformation and filtering in a single expression produces clean, readable code that's often more efficient than equivalent loops. Set comprehensions are essential for modern Python development, enabling concise data manipulation. The collections module provides specialized dictionary-like classes for common patterns. Defaultict automatically provides default values for missing keys, eliminating key error exceptions. When you access a non-existent key, it calls the provided factory function. Int returns 0, list returns an empty list, set returns an empty set. This is invaluable for counting and aggregation tasks. Counter is specifically designed for frequency analysis, tracking how many times each element appears. It provides convenient methods like most_common for finding the most frequent items. These patterns appear constantly in real-world applications. Counting words, analyzing user behavior, or grouping data. Learning to use these specialized classes dramatically improves code clarity and efficiency. Let's apply set operations to a real-world scenario. Deduplication. Sets provide the fastest way to remove duplicates, especially with large datasets. However, sets don't preserve order, which matters sometimes. The dict.fromKeys pattern elegantly solves this. It maintains insertion order while guaranteeing uniqueness. When combining data from multiple sources, set unions quickly identify all unique items. Performance matters in production. Checking membership in sets is O1, average case, while checking in lists is O(n). For a million-item list, this difference is substantial. Understanding these performance characteristics helps you choose the right data structure. Set-based deduplication appears everywhere. Cleaning user data, removing duplicate API responses, and processing log files. This practical knowledge directly impacts real application performance. Text analysis is a perfect real-world use case combining dictionaries and counters. Reading text, converting to lowercase, and splitting into words prepares your data. Using counter immediately gives you frequency counts with minimal code. Comparing different methods, counter versus manual dictionary updates, highlights why specialized classes matter. Filtering out common stop words refines your analysis, focusing on meaningful terms. Computing percentages and frequencies from the counter data requires dictionary comprehensions and arithmetic operations. This workflow appears in countless applications: search engine optimization, content analysis, chatbot training, and sentiment analysis. Mastering these combined operations enables sophisticated text processing and data analysis. The simplicity and efficiency of these approaches make them essential tools in any developer's toolkit. Performance matters in production applications, and data structure choice directly impacts speed. Dictionary and set lookups average O1 time complexity using hash tables, compared to ON for lists. When you have 100,000 item collections, this difference becomes massive: microseconds versus milliseconds. If you need frequent membership checks, sets outperform lists dramatically. If you need ordered data with fast lookups, sorted lists work, but dictionaries with any key type are more flexible. Memory considerations matter too. Sets and dictionaries use more overhead than lists for small collections but scale better. Understanding big O notation and actual performance characteristics helps you make informed architectural decisions. Writing fast Python code starts with choosing appropriate data structures. Investing time in performance analysis early prevents painful refactoring later. Even experienced developers encounter pitfalls with dictionaries and sets. Modifying a dictionary while iterating over it causes runtime error. Python prevents this because the iteration state becomes invalid. The solution is iterating over a list copy of keys. Shallow copy confusion trips up many. When you copy a dictionary containing lists or other mutable objects, the nested objects are still shared. Modifying nested structures affects both copies. Deep copy solves this, creating independent copies of nested objects. Using mutable objects as dictionary keys fails because dictionaries use hash values to locate keys, and mutable objects' hash values change when modified. Lists, dictionaries, and sets can't be keys. Use tuples, frozen sets, or immutable objects instead. These aren't exotic edge cases, they're common scenarios. Understanding and avoiding these pitfalls separates competent developers from novices. Real-world data rarely exists in flat structures. User profiles contain nested settings, configuration files hold hierarchical data, and APIs return deeply nested JSON. Working with nested dictionaries requires careful navigation. Chaining GET calls prevents key error when intermediate keys don't exist. Each GET returns the default, usually an empty dict, if the key is missing. This defensive programming approach is essential for robust applications. Traversing nested structures requires nested loops and conditional logic, often handled with recursive functions. Recursive approaches elegantly handle arbitrary nesting depth. Flattening converts nested structures to single-level dictionaries, useful for database storage or spreadsheet export. Understanding these techniques enables you to manipulate complex data structures confidently. Serialization, converting Python objects to storable formats, is essential in real applications. JSON is the standard interchange format, and Python's JSON module seamlessly converts dictionaries to JSON strings and back. The indent parameter makes output human-readable, crucial for debugging. Loading and saving JSON files is straightforward with load and dump functions. CSV files, common in data analysis, work naturally with dictionaries through dictreader and dictwriter classes, where each row becomes a dictionary with column headers as keys. However, JSON doesn't support sets or custom objects by default. For sets, convert to lists before serialization. For complex objects, implement custom JSON encoders. Understanding serialization enables you to persist complex data structures, interact with APIs, and share data across systems. These techniques form the foundation of data pipeline development. Dictionaries and sets are powerful tools for algorithm design. The twosome problem exemplifies this. Instead of nested loops checking every pair, ON superscript 2, using a set for O1, lookups reduces complexity to ON. This pattern, remembering seen elements in a set, appears throughout algorithm design. Anagram detection becomes trivial with counter, comparing frequency maps instantly. LRU, least recently used, caches leverage dictionary fast access combined with ordering to maintain both performance and capacity limits. These aren't academic exercises. They're fundamental patterns in real systems. Coding interviews heavily emphasize these approaches. Production systems use them constantly for caching, deduplication, and optimization. Internalizing these patterns elevates your algorithm design skills dramatically. Understanding when and how to apply these data structures separates developers who write functional code from those who write efficient, scalable systems. Let's consolidate everything we've learned. Dictionaries excel at key-value mappings with O1 lookups. Sets provide fast membership testing and automatic deduplication. Comprehensions create collections elegantly and efficiently. The collections module offers specialized classes like counter and defaultIct for common patterns. When designing systems, choose data structures based on access patterns. Do you need lookups by key? Use dictionaries. Need fast membership checks? Use sets. Need to preserve order while deduplicating? Use dict.from keys. These decisions compound over time. Small optimizations in data structure choice can multiply to significant performance improvements. Professional code consistently uses comprehensions, leverages the collections module, and chooses the right data structure from the start. Always consider, what are my common operations? What's my expected data size? What access patterns matter most? These questions guide optimal solutions. You now have comprehensive knowledge of dictionaries and sets. Practice these concepts with real projects to internalize them completely. Your learning journey doesn't end here. Python's collections module offers additional structures worth exploring. OrderDict provides explicit ordering and additional methods, though regular dicts maintain insertion order in modern Python. ChainMap elegantly chains multiple dictionaries for configuration management where local settings override defaults. Name tuples create lightweight, immutable structures more readable than plain tuples. Challenge yourself with practice problems. Implement custom dictionary subclasses, solve algorithmic problems using these structures, build data processing pipelines. Contribute to open source projects using Python, which forces you to handle real-world data complexities. Study production code to see how professional developers apply these concepts. The Python documentation is your reference. Mastering it accelerates your growth. Build projects applying these concepts. Data analysis scripts, web applications handling complex user data, CLI tools processing structured data. Consistency and practice solidify knowledge into skill. Keep learning, keep coding, and keep elevating your Python expertise. Congratulations on completing this comprehensive tutorial. You've journeyed from dictionary basics to advanced set operations, learned practical patterns from the collections module, and explored algorithm design. You understand when to use dictionaries, when to use sets, and how to combine them elegantly. You know the performance characteristics and can make informed architectural decisions. Most importantly, you have a foundation for tackling real-world Python challenges with confidence. Remember, expertise comes from consistent practice. Review challenging sections, work on projects, and continuously challenge yourself with harder problems. Join Python communities, read others' code, and contribute your own. The skills you've learned today are immediately applicable. Use them in your next project. Thank you for watching Elevate Learn. Subscribe for more tutorials on advanced Python, data structures, algorithms, and professional development practices. Keep coding, keep learning, and keep elevating your skills. See you in the next video.